how a capacitor is able to store electrical charge and thus electrical energy. Before we show how a capacitor does this, we will again show a brief demonstration on what a capacitor does and how you yourself can make a capacitor. What does a capacitor do? Here are three 1 farad capacitors connected in series, and here is a small light bulb. I connect the leads to the light bulb, and as you see, nothing happens. Next, I connect the capacitor to the 6-volt battery to charge it up. Okay, now I again connect the light bulb to the capacitor. As you can see, the capacitor now is charged up. Remember the question? It was this: what does a capacitor do? Well, as you just saw, a capacitor stores electrical energy. While this is true, a better way of saying the same thing is that a capacitor stores up electrical charge. We now show how to make a simple capacitor. First, we put a sheet of aluminum foil down that has a wire taped to it. Then, as an insulating layer, we use a piece of waxed paper. This is also called the capacitor's dielectric. Then we finally put a piece of aluminum foil on, which has another wire taped to it. And this is our capacitor, and the two wires are the leads.
This is the first of 5 drawings we will show, which help explain how a capacitor stores electrical energy. Here in figure 1, this is the capacitor. It consists of these 2 plates. By the way, in the homemade capacitor we just showed in the video clip, these plates are the 2 sheets of aluminum foil. While these plates here are relatively thick, this is only so I can draw the plus and minus charges in them. The extra plates are usually much thinner than the thinnest aluminum foil you can buy. In between the plates is the insulating layer referred to as the dielectric. Here it is shown in light greenish yellow. In a homemade capacitor, the dielectric is the wax paper. Here is a 6-volt battery. This is a switch which, when up as shown, doesn't allow electricity to flow. This here is a 3-digit digital voltmeter whose probes are connected to the 2 plates of our capacitor here. Now notice the voltmeter shows 0.00 volts. Keep in mind that a voltmeter simply measures the difference in voltage that exists between its probes. What 0 volts means is that the charge on both capacitor plates is the same, so there's no voltage difference between them. The drawing shows that there is the same charge on both plates. Since there are equal number of plus and minus circles on both plates, this means that the charge is also 0 on both plates. By the way, the blue circles represent electrons, which are negative charges. These electrons also are referred to as free electrons here, since they can easily move around the conductive plates. By the way, the ease that electrons can move about in something is the reason why that something conducts electricity. What are the positive charges? Basically, they are protons, which along with neutrons are located in the center, which is the nucleus of atoms. However, for several reasons, including the fact that protons are 2,000 times more massive than electrons, protons don't move around much. As this drawing indicates, the capacitor is discharged. This can be determined from either the voltmeter's reading or looking at the charges on the plates. In figure 2, we will show the conditions while the capacitor is charging. Figure 2 here shows the switch closed. This allows current to flow into the capacitor. It is assumed here that the switch was closed just moments ago. The voltmeter reading of 4.79 volts implies that the capacitor is nearly fully charged. Notice there is current flow taking place with the negative charges, electrons, traveling from the negative terminal of the battery through a wire, then through the switch, and then through the other wire and onto the left plate of the capacitor. Also, and this is very important, the electrons from the right plate flow through another wire and back into the positive terminal of the battery. Notice no charges actually flow through the capacitor, even though the negative charges flow into the capacitor's left plate through a wire, and negative charges also flow from the capacitor's right plate and through another wire. What is happening is that charges are building up on the capacitor plates, negative charges on the left plate and positive charges on the right plate. While the left plate becomes negatively charged and the right plate positively charged, there is no net buildup of charges in the capacitor itself, since the total number of negative charges and positive charges always remain equal in the capacitor. The thing that changes is that when the capacitor is discharged, the negative and positive charges on each plate are equal. However, when a capacitor is charged, not even fully charged any amount, one plate has many more electrons on it than the other plate, so it becomes negatively charged. This means the other plate must become positively charged in order for both the charges on the total capacitor to remain the same. Figure 3 here shows the fully charged condition of the capacitor with the battery still connected. Notice the switch is still closed. While the battery is connected, there is no current flowing. Why? Because the capacitor now has reached the same voltage, 6 volts, as the battery. Notice the electrons are now on the surface of the left plate. They are being strongly attracted to the other positively charged plate. I don't show the positive charges moving much, since they need much more force to move than electrons. Despite protons being stick in the mud, the positive charges do appear to move to the right, because the left plate's negative charges have repelled electrons, which leaves only protons, positive charges there. Remember, when you put one positive charge together with one negative charge, you get something with no charge. Keep this in mind. A plus 1 plus a minus 1 equals 0. And then from this no charge something, you kick out an electron, you wind up with a positively charged something, which means the net charge is now positive. Keep this in mind. If you don't add a minus 1 to a plus 1, you have a plus 1 anyway. Figure 4 here is probably the most interesting